Lesson 5, Variable Diagrams. Purpose of this lesson. When a computer is executing a program, you cannot see what the computer is actually doing inside. How does it actually do what the program tells it to? What happens as it executes each program statement? We need to find ways to understand what goes on inside that box we call a computer, and variable diagrams are a useful way to do that. We have seen variable diagrams in previous lessons. We give a short program below. First, work out what it does. Then draw a series of variable diagrams to show the successive values of this one, this one 2, and the other, after each of the lines 10, 11, and 12. Finally, state what the output of the program will be. Program to illustrate arithmetic operators include IOStream using namespace std, int main, int this one 2, const int the other equals 5, this one equals 3, that one equals 2, this one plus 7, divided by this one times the other. This one equals that one times this one divided by 9 plus 8. See out, this one equals this one. See out, that one equals that one, end L. See out, this one 2 equals this one 2. See out, the other equals the other, end L. Return 0. Test yourself. If you understood the simple variable diagrams that we drew in previous lessons, you ought to be able to complete this activity quite easily. Normally, if you manage to work out the solution to the main activity yourself, we suggest that you skip forward to the end of the lesson. However, we suggest that you now work through the discussion that follows. You will notice that we do not use this usual sub-activity or format for this activity, and that we tend to tell you the things more directly as usual. Activity solution. In the problem statement above, we suggest that you draw variable diagrams for lines 8 to 10, but to clarify the entire program, we will discuss it line by line from the beginning. Line 1, program to illustrate arithmetic operators. The compiler ignores everything after // since it is a comment. Comments are included so that the person reading the program can understand more easily what it does. Line 2, include IOStream. This line tells the compiler to include the names defined in the IOStream header file. Without this, the compiler will not recognize cout and endl. Line 3, using namespace std. This line tells the compiler to use the namespace std. It allows the compiler to recognize the names defined in standard header files like IOStream. Without the statement, we should prefix each of the names with std : Note that line 4 is left blanked to make the programmer easier to read for the programmer or for whoever else needs to read the program. Line 5, int main. This indicates the beginning of the main function of the program. Every C++ program must have a function called main. The reserved word int indicates that it will return an integer value to the operating system when the program terminates. This matches the statement return 0 in line 19. Line 6. The open curly bracket or brace indicates the beginning of the body of the main function. Line 7. Int this one, that one, this one 2. This line declares 3 integer variables called this one, that one, and this one 2. From this declaration statement, the compiler knows that it must set aside a separate memory position that can hold an integer for each of these 3 variables. None of these variables have a value yet. This does not mean that they are set to 0, but that their value is completely unknown or undefined. We can already draw diagrams for these variables and indicate these unknowns values with a question mark. Line 7, this one, that one, this one 2. Question mark, question mark, question mark. Line 8, const int the other equals 5. This line declares a constant called the other and gives it a value of 5. The reserved word const means that its value cannot be changed at any point during the program. We can draw the following variable diagrams for it. This one, that one, this one 2, the other. Line 8, question mark, question mark, question mark, 5. Discussion. There is an important difference between declaring a variable, as in line 7, and declaring a constant, line 8. When declaring a constant, we use a statement of the form const int constant name equals value. The const reserved word tells the compiler that the integer constant called constant name will have the value throughout the program, and that its value cannot change while the program is running. In fact, we generally use uppercase letters for constant names to distinguish them from variables. With this convention, the constant declaration would be const int the underscore other equals 5. Note how we use the underscore character to separate multiple words in the name of a constant. Line 10. This one equals 3. This line assigns the value of 3 to the variable this one. Variables that one and this one too will be given values later on in the program, and at the moment are still undefined. The constant the other keeps the same value throughout the program. The variable diagram therefore changes to this one, that one, this one, 2, the other. Line 10, 3, question mark, 5. Line 11, that one equals 2 times this one plus 7 divided by this one times the other. This is a more complicated assignment statement than the one in the previous line. We need to do a calculation to work out the value that will be assigned to the variable that one. To evaluate this line, we need to know the values of this one and the other. We can get both of these values from the variable diagram that we drew for line 8. In working out this value, we must also take care to follow the correct operator precedence, namely times and divide before either plus or minus, BODMAS. And of the left to right rule for operators of equal precedence. 2 times 3 plus 7 divided by 3 times 5. 2 times 3 is 6. 7 divided by 3, 2 times 5. 6 plus 10 equals 16. Notice that we have done the times and divide operation before plus, and that where divide came before times, we also use the left to right rule. This is termed operator precedence. If you feel unsure about this, look back at lesson 2. The next set of variable diagrams is therefore this one, that one, this one 2, the other, line 11. This one is 3, that one 16, this one 2, question mark, the other 5. Line 12. This one 2 equals that one times this one divided by 9 plus 8. Using the values in the diagrams for line 11, work out what value the statement will store in variable this one 2, and then compare it with the answer we give below. Note how the operators with the same precedence, times and divide, are evaluated from left to right. 16 times 3 divided by 9 plus 8. 16 times 3 is 48 divided by 9 is 5 plus 8, all equals 13. This gives us the next set of variable diagrams. In line 12, this one is 3, that one 16, this one 13, the other 5. The remaining lines of the program do not change the values of any variables, and so we do not need to draw any more variable diagrams. You should now have a clear idea of variable diagrams and how to draw them yourself. In later lessons, we will use variable diagrams again, but with more complicated problems. We've finished with the variable diagrams, but we have not quite finished with the program. What about lines 14 to 17? What do they do? We repeat them here. See out this one equals this one. See out that one equals that one. End L. See out this one 2 equals that one 2. See out the other equals the other. End L. Of course, these lines do not change the value of any variables. As you recognize from a previous lesson, the cout instruction displays certain values on the screen. Working from the final variable diagrams we have just completed, the computer will display this one equals 3, that one equals 16, this one 2 is equal to 13, the other equals 5. This one equals 3, that one equals 16, this one equals 2 equals 13, the other equals 5. Activity 5b. Type in the program below without the line numbers and test it out. Hint, press enter every time the program displays an instruction to see the next instruction. Think of a number, include iostream using main namespace std. Int main, int number equals 40, int answer, cout. Think of a number between 30 and 50, write it down, end L. Cout, Then do the following calculations on paper. End L. C in, get. C out, double it. End L. C in, get. Answer, number times 2. C out, add 29 to this. End L. C in, get. Answer equals answer plus 29. C out, double the result again. End L. C in, get. Answer times 2. C out, subtract the original number from your answer. End L. C in, get. Answer equals answer minus number. C out, divide the answer by your original number and throw away any remainder. End L. C in, get. Answer equals answer divided by number. C out, your final answer is answer. End L. Return 0. Draw variable diagrams to show the declaration of variables and to show how their values change. Test yourself. You should understand many of the lines of this program, as you've seen many of the statements before. There are a few lines that may seem rather strange. You should be able to get a good idea of what they do just by running the program. We give a number of sub-activities that give some further information on the new concepts used in this program. Predict the output of the following program. What's the output? Include IOStream using namespace std int main. Int I equals 13. C out I in L. Return 0. Say the declaration of variable I is changed to int I. Predict the output once again. If you're not sure about any of your predictions, you better type in, compile, and run the above program, because we aren't going to tell you what the output is. Discussion. There are some interesting things to note about this program, however. The statement int I equals 13 declares variable I and initializes it to 13 in one step. If we replace the declaration statement with int I, we have no idea what value I is. Remember that a declaration statement just sets a memory position aside for an integer, but that memory position can have some arbitrary value stored in it. If the program outputs the value of an uninitialized variable, the output is unpredictable. You generally use a question mark to indicate an uninitialized value in a variable diagram. Have you worked out what cin get does yet? Here is a sub-activity to confuse you if you think you know. Run the program of the main activity again, and this time type ABC before pressing enter the first time. Describe what happens. This time the program does not wait for the user to press enter between each instruction, but displays the next 3 instructions immediately before giving the user a chance to press enter again. Sub-activity 5.B. Write a program to input a number from the keyboard. The program must multiply the number by 2 and display the result. There are 2 restrictions on your program, however. 1. The program may only use one variable. 2. The program may not include an expression, in other words, with calculations in a cout statement. Sub-activity solution. Doubles number and displays the results. Include IOStream using namespace std int main. Int n, cout, enter a number. Cin, n. N equals n times 2. Cout doubled. N, end line, return 0. Discussion. Here we see an interesting thing. We are assigning a value to a variable which also appears in the expression on the right-hand side of this assigned operator. For example, the assignment statement n equals n plus 5 looks wrong. How can n equal n plus 5? It seems strange because it looks like a mathematical equation, but you must remember that an assignment statement is not an equation. It is an instruction to store a value in a variable. What happens is this. The computer first calculates the value of the expression on the right-hand side, in other words, n plus 5, using the original value of n. Then it assigns the result to the variable on the left-hand side, which happens to be n as well. The fact that this is the same variable does not matter because of the order in which things are done. Namely, first evaluate the expression and then assign the value. So this statement will add 5 to whatever is stored in variable n and store it back in variable n. Activity solution. The first statement in the program Activity solution. The first statement in the program that will memory allocation or change the value of variables is line 7. Line 7, int number equals 40. This declares a variable called number and initializes it to the value 40. We indicate this by means of a variable diagram as follows. Line 7, number 40. Line 8, int answer. This declares variable answer. Line 8, number 40, answer question mark. As stated above, we indicate that variable answer is uninitialized. In other words, it does not yet have a value by means of a question mark. It is unnecessary to initialize answer at this point because its value will be changed by the assignment statements later on. Line 9, 10, 12, 15, 18, 21, 24, and 27 see out end line. These are output statements like we've seen before. They have no effect on any of the variables. Line 27 outputs the final value of variable answer. Line 11, 13, 16, 19, 22, and 25 see in get. These statements appear to get the program to wait for the user to press enter. However, as subactivity 5b2 shows, it is more accurate to say that cin get removes one keystroke from the input stream cin. These statements have no effect on the values of the variables. Line 14, 17, 20, 23, and 26. Answer equals. These are assignment statements to calculate new values for the variable answer. Line 17, 20, 23, and 26 are interesting because variable answer appears both on the left-hand side of equals and in the expression on the right-hand side of equals. These lines have the effect of updating the value of variable answer. We could have declared 4 additional variables to store the values of each calculation, but this is not necessary. Using the same variable over and over saves us having to do so. We can indicate the change brought about by each assignment statement by means of a series of variable diagrams. Line 14, number 40, answer 80. Number 40, answer 109. Line 20, number 40, answer 218. Line 23, number 40, answer 178. Line 26, number 40, answer 4. Try changing the initial value of the variable number to any number between 30 and 50, and you will see that the output of the program remains the same. This shows that the calculations all give the same result no matter what the number the user thinks of. Discussion. A series of variable diagrams like those above are like a series of snapshots of the computer's memory. The photos are taken just after the program has executed the line as indicated. Drawing all these diagrams can be quite a bother since there is so much repetition. It would be easier to stand in front of a white blackboard and just draw one set of boxes. Then, as you step through the program, erase the values that change and write in new values. You could still write the line number in front of to help you to keep track of where you are. Important points in this lesson. Programming concepts. The purpose of this lesson was to show how variable diagrams can be used to work out what programs do, particularly as they get more difficult. Variable diagrams can also be a very good way of tracking down bugs which are difficult to find. We will come back to both of these aspects in future lessons. In addition to learning about variable diagrams, this lesson introduced the following concepts. We can initialize a variable while declaring it. This can be done in the format int variable equals value. We can declare constants to improve the readability and maintainability of our code. The format for a constant declaration is const int constant name equals value. When we declare a variable, we're telling the computer to set aside a memory position to store a value that will probably change during execution of the program. By contrast, when we declare a constant, we give it a value that will remain unaltered throughout the program. When we declare a variable, we may provide a value to initialize it, but when we declare a constant, we must provide a value. In many computer languages, a variable only has a value once it has been initialized. In other words, once the program actually assigns it a value. Before initialization, the value of a variable is undefined, and that is why we use a question mark in its variable diagram to indicate that its value is unknown and probably garbage. Programming principles. Remember to initialize variables. Declare constants wherever you can. Use uppercase letters for the names of constants to distinguish them from variables. If the name consists of more than one word, use the underscore character to separate the words. Example, const int days underscore of underscore year equals 365. If it becomes difficult to work out what a program does, draw variable diagrams. We indicate the value of an uninitialized variable with a question mark to show that the value is unknown. The following statements in a program have an effect on the variable diagrams we draw. Declaration statements. We draw a box for each variable and label them with their names. Input statements. We write the values input from the keyboard in the appropriate boxes. Assignment statements. We change the value in the box of the variable on the left-hand side to the value determined by the expression on the right-hand side. Exercises 5.1. Consider the program below and draw variable diagrams to show the value of each variable for statements and give the exact output of the program. Tracing practice include iostream, using namespace std, int main, int jkmn, j equals 3, k equals 2, m equals j times j minus 6 divided by k. N equals j times j minus 6 divided by k. Cout j, k, m, n, inline. Cout j equals m divided by 2 plus 3 times j. K equals j minus m times n. Cout j, k, m, n, inline, return 0. Exercise 5.2. Rewrite the solution to activity 5b using a constant instead of variable number, and using compound assignment statements as discussed in activity 4b in place of all the standard assignment statements. Then draw a series of variable diagrams to indicate that your program is equivalent to the original version.